Let's step onto the floor of the ABC company. Like any manufacturer, they have a singular objective: produce two specific products in a way that generates the highest possible daily profit. This production data shows the three physical realities that limit how much they can actually build. They are restricted to 1,575 pounds of raw material, 1,500 square feet of storage, and a maximum of 7 hours of daily production time. The financial pressure comes from the margins. Every unit of product I they ship out nets $13, while product 2 brings in $11. When you have three different constraints, space, weight, and time, all competing for the same two products, the right production mix isn't obvious. Guessing wrong means wasting warehouse space, burning through materials, or leaving expensive equipment idle. To find the solution, management uses a technique called linear programming. It is a mathematical method designed to calculate a specific production target based on those rigid physical limits. The process effectively replaces trial and error with a model that accounts for every restriction at the same time, ensuring no resources are wasted. To build this model, we convert pallets and hours into algebra. Product I is X1 and product 2 is X2. We want to maximize total profit, Z, which is $13 times X1 plus $11 times X2. However, that profit is subject to our factory limits. Storage space, materials, and production time are written as mathematical inequalities called constraints. Finally, we add non-negativity constraints, which tell the math we cannot produce a negative number of products. Once the physical floor is reduced to these rigid inequalities, the problem moves from a warehouse floor to a coordinate plane. With two variables, we solve this on a simple graph. Constraint inequalities are plotted as boundary lines representing physical limits. The overlapping space is the feasible region, showing every production mix the factory can actually make. While every point in this region is a valid choice, we are searching for the single coordinate that yields the maximum possible profit. According to the extreme point theorem, the optimal solution is always found at a corner of this shape. By testing these coordinates against our profit equation, we pinpoint the highest value, producing 8 units of X1 and 10 of X2. By identifying these geometric intersections, a company moves past a range of good options to find the exact production level that maximizes their limited resources. But the math doesn't always result in a neat, closed polygon. When the model breaks, it reveals deep flaws in a business's strategy. For example, redundancy occurs when one rule makes another irrelevant, like requiring a product to be at least 15 years old and at least 16 years old. One constraint is simply doing all the work. Infeasibility happens when management's requirements are so conflicting that the boundary lines never overlap. There is no shaded region, and therefore no solution. If a model is unbounded, the shaded region bleeds off the graph entirely. This usually means a critical constraint was forgotten, leading the math to suggest infinite, impossible profits. And in rare cases, we see alternative optimal solutions. This is when the profit line runs perfectly parallel to a constraint, giving management multiple different ways to reach the same maximum profit. These mathematical edge cases serve as a diagnostic tool. When geometry fails, it tells a manager exactly where operational assumptions are contradictory or incomplete. This precise geometric logic extends far beyond the walls of traditional factory floors, reaching out into completely different industries, like commercial agriculture. Farms use these same models to balance nutritional constraints. They calculate the exact blend of corn and soybean meal that satisfies protein and fiber requirements at the lowest possible cost. Computers apply this same logic to thousands of variables at once, efficiently routing global shipping fleets and seamlessly scheduling international airline crews. By defining our chaotic world through these mathematical boundaries, linear programming allows us to locate the absolute best decisions waiting at the corners of reality.